Hello everyone, my name is Nadia Amalia and I'll present the results of our work about a novel method to determine the glass transition temperature of polymers. So, understanding how objects or materials are deformed, dealing with fluxes or changes, is very important for applications in various fields. This is related to the importance of design stages of a structure to avoid failure. In our previous work, we proposed a method for estimating the elastic modulus of materials without direct contact with the materials. The fundamental rule underlying the method is by utilizing the effect of gravity to bend a cantilever slender beam. The bending profile or the bending shape governed by the material or structure depends on the material dimension and the elastic properties, and this relationship is well known as beam theory. And actually, the Eiffel Tower and Ferris wheel in the late 19th century were developed with the beam theory, which at the time the beam theory was also the enabler of the second industrial revolution. And for our purpose, we discretized this relationship. We firstly transformed the bending equilibrium equation in discrete form, and since we would face arbitrary bending angles, either small or large, the Euler-Bernoulli equation shouldn't be applied since this equation has been derived under assumption of small bending angles. And to allow large deflections, we consider Taylor expansion. Therefore, the elastic modulus of the G segment of the discretized bending beam can be measured with the following equation, and we examine several samples to determine the elastic modulus. And to further confirm the estimation results, we directly measured the samples, the elastic modulus of the samples with tensile tests, and our estimation deviates by about 12% from the measurement. This difference is likely acceptable since the measurement of the elastic modulus is generally not precise. For example, this obtained variation by 49% in measurement the elastic modulus of human trabecular femoral bone using nano indentation method. Lotz obtained variation by 61% for measurement of elastic modulus using compression method. Garnier obtained variation by 61%, and by vibrating a cantilever using an electromagnetic method, Yoshi et al. Reported a measurement of wire or strip can produce an error up to 35%. Therefore, the relatively small deviations in our measurements compared to the reference data are acceptable. And we also estimate the effect of temperature of the elastic modulus on the elastic modulus. And since the bending profile of the sample was recorded continuously during temperature rise, the proposed method allows continuous monitoring of the material modulus with temperature. And here, in this picture, the closed circles represent the calculated elastic modulus of PMMA at different temperature. We observe that the elastic modulus nearly unchanged at around 3 GPa when the ambient temperature was increased at up to 345 Kelvin, and above that the elastic modulus dropped rapidly to 1.7 GPa and down to 0.5 GPa at 368 Kelvin. And at the highest measurement temperature, the elastic modulus is around 8.9 MPa. And we find here that the reduction in elastic modulus when the temperature changes from the glassy plateau to rubbery plateau is around 2.5 order of magnitude. This is very close to the most accepted value of around 3 orders of magnitude, to mention that the dropping region is the glass transition region. And a phase transition from glassy to rubbery state induces a very sharp anomaly of the elastic modulus of materials. It is then interesting to inspect the equation that will describe the transition. In the case of phase transition at the boundary of solid and melted, Kahn's model well describes the process of motion of the boundary from solid to melted in the process of melting, or from melted to solid in the reverse process. Kahn has approximated the value of the parameter using hyperbolic tangent function as a function of position, and the hyperbolic tangent equation has generally been selected to describe the phase transition of collective system, such as the transition of magnetization in Ising model. Since we have considered the change of elastic modulus on temperature as a phase transition at the boundary in the temperature coordinate, we propose the similar equation tangent hyperbolicus for describing the variation of elastic modulus around the transition temperature. And to justify our estimation results, we also directly measured the glass transition temperatures of the polymer samples and obtain a consistency between the calculated results and our experimental observation. And we also check the accuracy estimation and found that it has we are very confident that the accuracy is acceptable. And so it is pertinent to mention that this is the first attempt for estimating the glass transition temperature of polymers based on the bending cantilever cylinder beam by the simplest method. Thank you.